As we have seen in the previous part, so we encounter spurious oscillations in the solution as the advection field dominates. That is, as we reduce the diffusion coefficient. Okay, we expect the same if you increase the advection velocity. So that is, as the petrolette number increases, we expect spurious oscillation. This is the inherent characteristics of the standard Elarton method. Okay, so this, when we apply the method to non-self adjoint PDEs, that is PDEs which do not result in symmetric matrices, which are not M matrices, then as we have seen in the 1D case, we end up with spurious oscillation. So to fix this, we add a stabilization. So we use the same stabilization that we have used in 1D, that is, we use the SUPG stabilization. This is streamline upwinding Petrov-Delarkin stabilization method. Okay, now, so here what we do, we add an extra term to the wheat form. Okay, so wheat form with stabilization, the first two terms are the terms from our wheat form. Okay, and this third term in blue is the extra term coming from the stabilization. Again, here notice we apply the stabilization at the element level. Okay, so here R is our residual, the residual of the PDE. Tau is the stabilization coefficient, stabilization constant, and P is the term. Okay, for the P is the term which is a function of the basis function W, sorry, the test function W, and we have a varieties of P, and for SUPG method our P is A dot del W. Okay, for different types of stabilizations we have a different P. For example, for Delarkin stabilization we use the residual itself as P, so instead of U we have W, and then we have a least square stabilization, Delarkin least square stabilization. Okay, but we stick to the SUPG method in this case. So P of W is A dot del W, and once we use R, okay, this is our R, the residual of the PDE. Once we make use of R and split the integral and take F. Okay, notice here, so when we use R in this integral, P of W is applied multiplied by F, and we know F, so F goes to the right hand side. Okay, so we get an additional term on the right hand side. Okay, so this term inside the bracket is our P. Okay, P of W, tau, and multiplied by tau multiplied by F. And on the left hand side we have P of W and A dot, okay, so A dot W multiplied by U. This is the advection term. We don't take the diffusion term, we ignore the diffusion term because for linear elements, which is what we are implementing at the moment, okay, so the 4-noded element which is a linear element, the second derivative is 0. Remember, this is the second derivative. For stabilization terms we do not transfer the derivative, okay, because P already has a derivative of W. Okay, so we do not transfer the derivative, we keep all the higher order derivatives in the residual as they are. Okay, and if we use a linear element, then the second derivative is 0, so we ignore this term, the diffusion term in the, okay, we ignore the diffusion term in the stabilization for linear elements because it is 0, since the second derivative for linear elements is 0. If we use higher order elements, then we do need to keep the diffusion term in the stabilization, otherwise we will not get consistent results. Okay, but that's a topic for another day, maybe in the future. Okay, but for this lesson we stick to linear elements. Okay, so we get one additional term on the left hand side and one additional term on the right hand side. Okay, this is from the stabilization, SUPG stabilization. And once we change this with form with like dot products to vector form, so if we make use of vectors, then Okay, so then we can write them like this. Okay, so again, like it's very similar to what we did in the case of the advection. Okay, so here a dot nabla becomes a nabla. Okay, because this del u is a 2 by 1 vector. So in order to get that in order to get a scalar, when we multiply all these terms, okay, we have to use the consistent dimensions for a and del w del u. Okay, so once we rewrite this term in the vector form, this is what we get. Similarly on the right hand side, and then we use the discretization. Okay, we apply the discretization and then we calculate the stiffness, like contribution to the stiffness matrix. Okay, so we have the distributions and their derivatives. Okay, so then when we substitute in the weak form and by looking at the element wise computations, okay, so this is our additional term for the stiffness matrix, the element stiffness matrix. This is the additional term to the element force vector. Okay, now the key question here is what is tau, our stabilization constant. Okay, so this is a really like quite a vast topic because the way and what we choose for tau affects a lot. It affects the accuracy of the results, it affects the convergence, it affects the matrix solvers that we can use. Okay, so there are it's a, like there has been a lot of research on finding the optimal values for tau. Okay, so we have constants, we have function, we have terms for tau that are functions of the solution itself, making the formulation nonlinear. Okay, so there are varieties. You can refer to the papers or the textbooks that I have suggested for this course. So okay, so in this lesson we are going to use some simple versions for the sake of implementation to see how they work. Okay, so the stabilization parameter. Okay, the first criteria is that the stabilization parameter should vanish with the mesh refinement. As h, that is the element size, goes to 0, we should not be required to use the stabilization. Okay, that is the primary criteria for selecting tau. Okay, like I said, there are a variety of expressions available for tau. The simplest one is the one we have used in 1D. Okay, so if these expressions are not valid for the combined case of advection and diffusion, because one is depends on mu and the other one depends on a. Okay, if you have both terms or if you have only one of the terms, then we cannot calculate the stabilization term effectively. For example, we have implemented this code for advection-diffusion and we use only the first term. Okay, and say we used only the first term, then if mu equal to 0, that is when we have pure advection, then we don't have a way to calculate tau. Tau is going to be infinite. So what we need a way to calculate tau for every case. So what we do, we combine these two and then, okay, so we use this expression for calculating tau. Okay, so here since a is a vector, we take its magnitude. Okay, here a is a vector. Okay, I forgot to make it bold. Okay, so a is a vector, so we take its magnitude. Okay, this is the term we use for calculating the stabilization term, and these are the two extra terms for the stiffness matrix and the force vector. So what we do, we go back to our code.